Hello dear students, welcome you all. So in this lecture I am going to discuss about the statistical definition of entropy. Statistical definition of entropy, right? So we have already discussed that what is entropy, and we have found a relation for change in entropy. ds is equal to delta q upon T, right? So this relation is basically a thermodynamic relation, right? And we have seen what is the meaning of entropy in terms of thermodynamics, right? In thermodynamics, entropy tells us about the amount of disorder present in a thermodynamic system, or we can say it represents the amount of energy unavailable for doing useful work, right? So this is the meaning of entropy in case of thermodynamics. Now we know we have thermodynamics linked with the statistical systems, so we do want a definition for entropy in case of statistical physics also, right? So we have already discussed the all branches of statistics. We have, Maxwell, Boltzmann, Fermi-Dirac, Bose-Einstein, all, and we have derived the distribution laws. We know very well that in all distribution law we have one equation in common, that was d log of EW, right, minus alpha dn minus beta du is equal to 0. While deriving the distribution law for Maxwell, Boltzmann, Bose-Einstein and Fermi-Dirac distribution law, we come across this equation, right? So this is the basic equation in all three wings of statistics, right? Now here, if we consider a system in which n is equal to constant, right, in that case we can take dn is equal to 0, right? So this equation in that case will become log of E W minus beta du is equal to 0. We already know what is the meaning of alpha, beta, n and u. Alpha, beta are constants, n is the total number of particles, u is the energy, right? Now this equation becomes this. We also know from all wings of statistics that beta is equal to 1 upon k t. Here k is Boltzmann constant. So if I put beta is equal to k upon t here, this equation becomes, right, d log of E W minus du upon k t, right? So if I rearrange this equation will become d log of E W is equal to du upon k t, right? So if I took this k toward this side, it will become d log of E W multiplied by k is equal to du upon t, right? And this is equation number 1, right? We know from the first law of thermodynamics. What is first law of thermodynamics? dq, I have to write it in terms of delta q, exact form of first law of thermodynamics, is equal to du plus dw. I have told you why we take delta here, not d, because it is not a exact differential, perfect differential, clear? So it can be written as du plus p dv. So when we added delta q amount of heat in the system, then this heat is utilized in two ways, in increasing the internal energy of the system and in doing the work. Let the total volume of the system or the gas under consideration remains constant. So dv will be equal to 0. It means delta q is equal to du. So I am going to put it in equation number 1. When you will put it here, you will get d log of E W is equal to delta Q upon T. Now what is here K was also multiplied. So as K is constant, so I can take it inside this bracket, right? It will make no change. K log of E W is equal to delta Q upon T. So this is this is equation number 2, right? So equation number 2 is the same as equation number this, right? You can see here it was ds is equal to delta Q upon T. So these two equations, this one and this one, they are symmetrical. They have same a thing on the right hand side. You can see delta Q upon T, here delta Q upon T. It means ds should be equal to this thing. So if we compare ds is equal to d K log of E W, then what we found? We found S is equal to K log of E W, right? What is S? S is a entropy. Clear? So this is the statistical meaning of entropy. S is equal to K log E W. That this is equation number 3. So this equation gives us the statistical definition of entropy. You can see here that statistically entropy is equal to some constant into log of W. Clear? What is W? W stands for thermodynamic probability. Right? Thermodynamic probability. That means number of microstates in a given macrostate. Right? So this is the statistical meaning of entropy. You can say that from this equation S directly proportional to W. Right? If the value of W is small, then less disorder in the system. If the value of W is high, then it means high value of S, high disorder in the system. And you can I mean have examples of all the cases that we have discussed. When we distributed 4 particles in 2 compartments, right? Let's take the case of a 2 compartment. We have distributed 4 particles in 2 compartments, right? This is compartment number 1 and this is compartment number 2. So when you know very well, when we distributed 4 particles A, B, C, D in these 2 compartments, there are different possibilities. We have total 2 raised to power 4 means 16 possibilities are there. So if you look at the different macrostates, we have 4 0 macrostate, 0 4, right? Then 2 2, right? Then 1 3 and 3 1. These all are the different macrostate. You know very well all these macrostate have different values of W, right? Because 4 0 will have only one distinct arrangement, one microstate. So for 4 0 W is equal to 1. For 0 4 again W is equal to 1. But for 2 2 W is equal to 6, right? For 1 3 and 3 1 it is equal to 4. You can recall that article, right? Now what does it means? It means W is equal to 6. W is equal to 6 is when we have 2 2. 2 2 means 2 particle here, 2 here. A, P, C, D. Similarly you can have C, D, A, B, all like that, right? 6 possibilities are there. It means in this particular case, right? In this particular case, you will have a maximum disorder, right? 2 2. It is clear that the 2 2 for the 2 2 configuration, you will have maximum value of W. It means you will have maximum value of entropy, and it is clear from this diagram that when we have 2-2 configuration, means 2 particle in 1 and 2 into, maximum disorder is there, right? Entropy is maximum. When the entropy will be minimum? Entropy will be minimum when W is minimum. W is minimum when this possibility 40 or 04. So you can see 04 means no particle here, all 4 particle there. Either 4 particle here, no. So it means minimum entropy, right? We have minimum distinct arrangements, right? Minimum disorder in the system. So it is very clear that statistically entropy is linked with the thermodynamic probability W, right? So this equation gives us a very important result, right? So now we can state entropy both in terms of thermodynamics as well as in terms of statistical physics, right? Now if I talk about the units and dimensions, S is equal to K log of E W. Now W is what? It is probability, right? Thermodynamic probability. It is having no units, no dimensions, right? It means S will have same units as of K, right? K is what? Boltzmann constant, right? And its units are Joule per Kelvin. It means the entropy will have same units as we have discussed earlier. That was ds is equal to delta Q upon T, Joule Kelvin. So it again give you Joule per Kelvin. So same thing you get here. It means whether you define entropy in this way or you define entropy in this way, the same thing is there, right? But the way of making a statement or way of saying the thing is different. Here you are saying it in terms of thermodynamics, and here you are stating it in terms of statistical physics, right? Now we can further extend this discussion and we can show that entropy is additive in nature. I mean, if we have different number of systems, right, that are actually the part of a large system, then this is a large system which is further divided into different subsystems, right? Like this is system number 1, this is system number 2, this is system number 3, so on. Then we can say that entropy of this entire system S will be equal to entropy of first system plus entropy of second system plus entropy of third system. This is called additive nature of entropy. Entropy get added when we have a large system and when we divide this system into small subsystems. To prove it, let's consider we have these 2 systems, right? Or even you can consider 3 systems, right? Let this system having in this system we have large number of particles distributed and it has thermodynamic probability W1. Similarly, this has thermodynamic probability W2. This has thermodynamic probability W3. So if I look at the thermodynamic probability of all the these 3 systems collectively, I mean the thermodynamic probability of this entire system, then W should be equal to the multiplication of all these individual thermodynamic probabilities, right? This is the rule in case of the theory of probability. So if I multiply this equation, all these together, then I will get W1, W2, W3 is equal to W, right? Now taking natural log on both the sides, what I will get? Log of E W is equal to log of E W1 plus log of E W2 plus log of E W3, right? So I get these 3 equations. Clear? Not 3 equations, sorry, I got this equation in which I have these 3 terms, different terms. Now what I do? I multiply this, let this is equation number 1. I multiply this equation number 1. This is equation number 1 for this subsection of this article. Here we are proving additive nature of entropy. right? So now I am going to multiply equation number 1 by Boltzmann constant K on both the sides. Clear? Right. So what does it becomes now? Right? I can say it is S. Right? And we know S is equal to K log E W. Yeah. So what does it mean? It becomes the entropy of the total, this complete system, right? So S is equal to, what is it? S1 subsystem, right? S2 subsystem 2, subsystem 3, right? And this. So here I have proved that when I have a large system, I divide this into subsystems, then the entropy of the large system should be equal to the entropy sum of the entropy of the individual systems. So this shows that entropy is additive in nature. Or if I have large number of subsystems, then I can write S is equal to summation of I go from 1 to n S I, right? So this is called additive property of entropy, right? So this is all about it. We have discussed about the statistical meaning of entropy in this article, and then we also proved that statistical point of view says that entropy is additive in nature, right? So thank you very much.